Let's consider a complex number, x plus iy. The real part of the complex number is x, and the imaginary part is y. Both x and y are real numbers. We know that an ordered pair of real numbers can represent a unique point in an xy plane. Let's consider an ordered pair x, y, which is represented by point P in the xy plane. If this complex number corresponds to the ordered pair x, y, then it can be represented by the unique point Px, y in the xy plane. Conversely, each point in the xy plane represents a unique complex number. In the figure, each point in the xy plane represents an ordered pair corresponding to a complex number. A plane having complex numbers corresponding to each of its points is called the complex plane or the argand plane. In the argand plane, the x-axis is called the real axis and the y-axis is called the imaginary axis. The x-coordinate of a point corresponds to the real part and the y-coordinate corresponds to the imaginary part of a complex number. For point P, 8, 6, 8 corresponds to the real part and 6 corresponds to the imaginary part of the complex number 8 plus 6i. All the points on the real axis are represented in the form x, 0, corresponding to the complex number x plus 0i. Similarly, all the points on the imaginary axis are represented in the form 0, y, corresponding to the complex number 0 plus iy. Let's consider the complex number 8 plus 6i. Point P, 8, 6 on the argand plane represents the complex number 8 plus 6i. Now, we'll draw perpendiculars from the point to the axis. The perpendicular distance of point P from the x-axis is 6 units, while the perpendicular distance of point P from the y-axis is 8 units. Therefore, the distance of point P from the origin O is the square root of the sum of 8 squared and 6 squared. This is equal to 10 units. The distance of point P from the origin is the modulus of the complex number 8 plus 6i. As you can see, this is the same way in which we calculate the modulus of a complex number. Therefore, the modulus of complex number z equal to x plus iy can be geometrically interpreted as the distance of point Px, y from the origin in the argand plane. Let's represent the conjugate of complex number 8 plus 6i. The conjugate of the complex number is 8 minus 6i. This complex number corresponds to the ordered pair 8, minus 6. Point Q, 8, minus 6 in the argand plane represents the conjugate of the given complex number. Here, it is observed that point Q is the mirror image of point P. In the argand plane, complex number z equal to x plus iy is represented by the point x, y, and its conjugates z bar equal to x minus iy is represented by the point x, minus y, which is geometrically interpreted as the mirror image of the point x, y on the real axis. We know that complex number z equal to x plus iy can be uniquely located in an xy plane by locating the ordered pair x, y. Let's draw a line joining point P and the origin. Let the length of the directed line OP be r, which is equal to the modulus of the complex number z. Let theta be the angle that OP makes with the positive direction of the x-axis. The complex number z can also be uniquely located in the xy plane by the ordered pair of real number r, theta. The coordinates r, theta are called the polar coordinates of point P. The origin is considered as the pole and the positive direction of x-axis is called the initial line. Let's establish a relationship between the Cartesian coordinates and the polar coordinates. Let's draw a perpendicular from point P to the x-axis. The length of PM is y units and the length of OM is x units. By using trigonometric ratios, cos theta is equal to OM divided by OP, which is equal to x divided by r. Therefore, x is equal to r cos theta. Sin theta is equal to PM divided by OP, which is equal to y divided by r. Therefore, y is equal to r sin theta. By using these results, the complex number z equal to x plus iy can be written as r cos theta plus ir sin theta. By taking r as common, we get r multiplied by cos theta plus I sin theta. This is called the polar form of the complex number. Here r is equal to the modulus of z, which is equal to the square root of x squared plus y squared, and theta is called the argument or amplitude of the complex number. We know that sin theta divided by cos theta is equal to tan theta, which is equal to y divided by x. Therefore, theta is equal to tan inverse y divided by x. This implies that argument theta of a complex number can only be defined for non-zero complex numbers. For any non-zero complex numbers, we commonly consider the value of theta such that minus pi less than theta less than or equal to pi, called the principal argument of the complex number, unless specified otherwise. Here are some properties of arguments. Argument of z1 multiplied by z2 is equal to argument of z1 plus argument of z2. Argument of z1 divided by z2 is equal to argument of z1 minus argument of z2.